To most of you, I assume, functional programming is difficult because it is so different from the programming language you know, like JavaScript or Python or Java or C or C++. So here I want to focus on what is simple about functional programming languages, and that is their computational model. For an example, I wrote down a mathematical definition of the Fibonacci numbers. The only thing we need to know about this is that the third equation, the third case, is only supposed to apply to numbers n that are not 0 or 1. So n in the third equation is assumed to be greater or equal to 2. Otherwise, these two equations are just exactly the mathematical definition of the Fibonacci numbers. But they are also a Haskell program. So this is the first sense in which functional programming is easy. We just write down the mathematical equations and they are already a program. By the way, this is the reason why sometimes functional programming languages are called declarative programming languages. We just declare, we just describe the problem, and that's already a solution. The second sense in which functional programming is easier than imperative programming is that the computational model is just replacing equals by equals, as we've done in high school algebra when we learned how to compute with numbers and variables and letters. So to make this to explain this in detail, let's just see how to compute, say, Fibonacci of 6. So what is the operational meaning of these equations? How are they a program? What are the steps, so the operational steps taken when we compute Fibonacci of 6? So as I said, the idea is that at each step in the computation, we apply one of the equations and we just replace equals by equals. So let's apply the third equation. We can say, oh, n is 6, right? So this is called pattern matching. On the left-hand side of the third equation, we have the pattern fib of n, and we can match the n against the 6. And so then we can replace fib of 6 by the right-hand side of the equation, where n is now 6. So 6 minus 2 is 4, plus fib of 6 minus 1 is 5. And actually, in functional programming in Haskell, we don't need to put the parentheses. Oh, my eraser is a little bit too big. Okay, so let me just put the 4 back and the 5 back. So I wanted to have fib of 4 here and fib of 5 here. Okay, and from now on, that's the recursive aspect of these equations. We just keep on doing the same thing. And so it doesn't actually matter really whether I continue with replacing fib of 4 or fib of 5 by its right-hand side, but let's do fib of 4. So this is fib of 4 minus 2 is 2, plus fib of 3, and we still have to do the plus fib of 5, right? We shouldn't forget about this. If you want, we can do parentheses around this here to indicate that we replaced the fib of 4 by fib of 2 plus fib of 3. And now we keep going on like this. So, for example, let's replace fib of 2 by fib of 0 plus fib of 1. And then we have still the fib of 3 around and the fib of 5 around. And now something new happens. We can stop the recursion now and go to the so-called base cases. So the first two equations tell us that fib of 0 is 0. And let's do two steps in one now. We can also replace fib of 1 by 1. So now I'm doing two steps in one. So if I was really pedantic, maybe I should break this up into two lines. And now again something new happens. So we use the arithmetic now. Now we don't apply any of the three equations, but we know that we know how to compute 0 plus 1. So I use an equation which I didn't write down. So I'm still using equations, right? So let me put this here on the left. So now I'm using the equation 0 plus 1 equals 1. And so on it goes. I think I can leave the rest to you.